We'll continue the discussion about optimal climate policy by looking more closely at the role of time discounting, starting with the Ramsey rule. The Ramsey rule. So let's define the net present value of receiving $1 in t years' time is e to the power minus rho t, and let's call this epsilon. Now this may not be the discount rate that, or the discount factor that you are used to looking at. You may be much more familiar with this expression here, 1 over 1 plus r to the power t, or 1 plus r to the power minus t. This is what we typically use when we calculate the net present value of something. Now if you let the time step shrink in this equation here, or in this equation here, if you let the time step shrink to 0, this expression converges to this expression. Why do I want to work in continuous time with infinitesimally small time steps? Actually, the math is easier in continuous time than in discrete time. Now, discounting is essentially an indifference equation. Essentially what you say, well, I want to make this investment if my return, which is in the future, is at least as valuable as the investment today, right? So that is what you want to do. So you want to equate the utility of receiving $1 in the future to having epsilon dollars today. And so how does this work? The value of epsilon dollars today is that epsilon times the marginal utility. This is du dc at time 0. So this is your utility gain of epsilon dollars today. This is the utility gain from $1 in t years time. So here we have the $1. We multiply it with the marginal utility, the u dc or u sub c at time t. So this is your marginal gain in utility of $1 then. And that we multiply with the value of future utility, and we denote that at e to the power minus rho t, where rho is your pure rate of time preference. This is essentially your discount rate of utility. Now, this expression can be rewritten by bringing u sub c to the other side of the equation. Now, if we assume a CRRA utility function, then the UDC or u sub c is c to the power minus eta, where eta is the curvature of the utility function. It's still not there because we have a CT and a C0, but CT is essentially relative to today's consumption, is essentially the growth rate, is essentially today's consumption times the growth rate of consumption. So we can write CT as C0 times e to the power GT, that's the growth rate of consumption, and G is the average growth rate, and T is the period at the length of the time that has passed. But then we have to raise that to the power minus eta G, and that is where the minus eta pops up. Now, good thing is that we now have C0 to the power minus eta T on both sides, so that cancels. And what we have is that the expression that remains is e to the power minus rho t minus eta gt. That by definition is equal to our money discount factor, e to the power minus rt. We take the log on both sides of the equation and we drop the minus signs, and we have the Ramsey rule that says that the money discount rate is equal to the utility discount rate, or the pure rate of time preference, plus the growth rate of consumption times the curvature of the utility function. Now, how does the eta g work? Why does this pop up, and what is the intuition behind this? Let's look at the utility function. We have consumption on the horizontal axis, we have utility or happiness on the vertical axis, and then the red curve is your utility function. Now, what is saving? Saving means essentially that you do not consume your money today, but you save it for later, and you increase your consumption tomorrow. So you reduce your consumption today, in order to increase your consumption later. Now, what is the trade-off that you make in utility terms? Well, if you reduce your consumption today, you lose utility. That is a loss. In return, you gain consumption tomorrow, and as a result, your consumption, your utility tomorrow increases. Now, in the graph that you're looking at now, the horizontal distances are equal. So the assumption here is that there's no interest. And if you further assume that you expect to be richer in the future, then this is a bad deal, right? Because if you expect to be richer in the future, then the utility loss from saving today is smaller than the utility gain from increasing your consumption tomorrow. So really, in order for us to be indifferent between the two, what we need is that the vertical distances are equal, that your utility gain tomorrow is equal to your utility loss, exactly compensates your utility loss today. And that implies that the horizontal distance is much larger, and that is your eta, G. Your eta measures the curvature of the utility function, so that is why your eta is important. Your G is important because it measures how fast you are moving to the right, how fast you are growing richer. It is important to note that derivation of the Ramsey rule that I have just given is all from a consumption perspective. There's of course an alternative interpretation of the interest rate, and that is the opportunity cost of capital. Now, in the same paper that he derived this particular rule, Ramsey also showed that in a dynamic equilibrium, the opportunity cost of capital and consumption rate of discount are equal to each other. So it's just two sides of the same coin.